Okay, we'll start now. So, in the acceleration in mechanism, am I audible to all of you?
Yes, sir.
Hmm. So, we can write in kinematics of machines, in kinematics of machine, acceleration, acceleration of a mechanism is quite important aspect.
Sir, screen sharing.
Okay, just a second. Is it visible now?
Yes, sir.
Yes.
Aspect as well. So, how to find out acceleration of a link? Okay, acceleration of a link. Suppose we take any arbitrary link and we'll choose 2 points on it, A and point B. So the distance AB is fixed and the relative velocity of point B with respect to A is known to us, okay, by direction and by magnitude, and omega is the angular velocity, alpha is the angular acceleration. Am I clear? Someone has switched on the audio, please switch it off. Okay, so this is the condition. Now consider 2 points, sorry, consider 2 points A and B on a rigid link, as shown. Let this point B moves with respect to A with an with an angular velocity omega radian per second, and alpha is an angular acceleration is, I can say, alpha radian per second square. Okay, now the acceleration of a particle, we can say whose velocity changes in both magnitude and direction at any instant has the following components has the following components. So first component is centripetal or radial component. Okay, remember this, centripetal, or it is known as the radial component which is perpendicular to the velocity of the particle, perpendicular to the velocity of the particle at given instant. Okay. So this radial component is always perpendicular to the velocity of the particle. Okay, or you can say it is along the link. If we are telling perpendicular to the velocity of the particle, this is the velocity, and if it is perpendicular means it is along this link. Am I clear? The radial component.
Yes, sir.
Okay, and the second component is the tangential component. Tangential component. It is parallel to the velocity of the particle at a given instant. At a given instant. So therefore for link AB, velocity the velocity of point B with respect to A, that is BA, is perpendicular to AB. Now point B moves with respect to A with an angular velocity omega radian per second. Okay, so therefore the centripetal, or we can say the radial component of the acceleration of point B with respect to A, that is represented by, remember, okay, BA, acceleration of point B with respect to A, and here superscript R represent the radial component, is equal to omega square multiply with link length AB. You remember this formula. It is omega square of the link length, radial component. So we can say ABA of R component is also equal to B square BA by AB. ಎಡಕ್ಕೆಂತಿಲ್ಲ, because we know that omega is omega, I can say BA is equal to BA by AB, isn't it? So if we're telling omega square BA, it is B square BA by AB square, isn't it? So this, if you multiply with AB, okay, so your ARBA will be equal to B square BA by AB, because this cancel out. So we get ARBA is equal to B square BA by AB. So you remember this. Am I clear?
Yes, sir.
So this radial component of acceleration acts perpendicular to the velocity VBA, or we can say parallel to link AB. Now tangential component. First we are finding out the magnitude. Okay, then we'll see how to get them graphically. Now the tangential component of acceleration is represented by A B A superscript T, okay, which is equal to the angular acceleration alpha multiplied by link length AB. Remember this. Okay, so we can say A tangential B to A is equal to alpha multiplied with AB. So in this way you can find out both the radial and the tangential component. And this tangential component of acceleration acts parallel to BBA, or we can say or you can say perpendicular to link AB. Okay. Now procedure to draw the uh, acceleration diagram. Procedure to draw acceleration diagram. So the first step is uh, you choose a reference point. Uh, Suppose I choose one reference point x here. Okay, let's say x is the reference point. Okay, we know that the radial component is parallel to the link in other sense. Okay, you remember in one way only. If we are considering link, then the radial component is always parallel to the link and the tangential component is always perpendicular to the link. Okay, this way you can remember. So we'll draw from point x the tangential component which is always perpendicular to the link. So it will be in this direction. Okay, so it is ATBA, the tangential component, and also the radial component will be in this direction. Okay, direction is very important. It is ARBA. Okay, and so this point is B dash, this point is A dash. Now, if you join A dash B dash, you will find out the total acceleration component of B with respect to A. Am I clear?
Yes,
Yes,
sir.
sir.
So, first step is from point B dash. Okay, draw B dash X. Okay, starting point is B dash here. Remember, huh? B dash X parallel to link BA. Okay, representing the radial component of acceleration of point B with respect to A, that is your A radial B to A. Then from point X, sorry, to from point X, draw X A dash, okay, which is perpendicular to link, can say BA, representing the tangential component of acceleration, tangential component of acceleration of point B, of point B with respect to A, that is A tangential B to A. Okay. Third step is join A dash B dash, okay, known as acceleration acceleration of link AB representing the total acceleration acceleration of point B with respect to A, that is your A subscript BA. Okay, this is the way to draw the acceleration diagram. Now the next is acceleration of a point on a link. Like earlier we used to find out velocity of a point on a link. Here we'll find acceleration of a point on a link. Now, this is very important. Now consider any 2 points on a link. Let's say this is the link. We'll consider any 2 points. This is point A. This is point B. Now the relative velocity of point B with respect to A is BBA, which is perpendicular to AB. We all know. Okay. Now here we can write, consider consider 2 points A and B on a link. Let the acceleration let the acceleration of point A, that is, you can say small a subscript capital A, known in magnitude and direction. Direction of path B is given. Okay. Also, the direction path of, you can say, point B is given. Let's say we can draw here. Let's say this is the path of point B. It is given. Okay. Here you can write path of point B. So here point A acceleration magnitude and direction is known to us, and point B path is given to us. So the acceleration of point B is is determined in in magnitude and direction by drawing the acceleration diagram as follows. So we'll follow the following steps. Okay, first is, mm, from point O dash, from point O dash, reference point is O dash, vector draw a vector O dash A dash parallel to the direction of absolute acceleration acceleration at point A, at point A, that is A A. Okay, to some scale, to some scale. So we'll take a reference point here. You can see we'll take a reference point O dash here. Sorry, it is O dash, and we'll draw a line. Okay, which is the absolute acceleration of point A known to us in magnitude and direction. So we'll get point A dash. Okay. Now the next step is acceleration of point B acceleration of point B with respect to A has two components. Has two components, radial and tangential. Radial and tangential. Okay, so draw vector, draw vector a dash x, okay, parallel to link AB, okay, representing which component? Representing radial acceleration. Radial acceleration component, that is A radial BA, that is B square BA by AB. Okay, so we'll draw A dash X. Okay, we'll draw a dotted line. Let me change the color here. A dash X. Okay, A dash X. Okay, which is parallel to the link AB. Okay, representing the radial component of acceleration of point B with respect to A. So A dash X. Now its magnitude we can find out from this relation. Okay, from this relation, and accordingly we'll draw as per the scale. Okay, A dash X. Now next step, from point X, from point X, draw uh, x b dash, okay, vector x b dash vector, which is perpendicular to link AB and through O dash, and through O dash draw a line parallel to the path of B, representing absolute acceleration of point B, that is A B. Okay, so the two vectors intersect at B dash. Okay, now the value of acceleration of B and the tangential component AT BA may be measured to the scale, to the scale. That means from here in this diagram, what it says, you draw a line perpendicular to link AB, okay, whose magnitude we don't know, only direction is perpendicular to the link. Draw a line, and from O dash you draw a continuous line, sorry, a continuous line parallel to the path of your point B. Okay, so they will intersect at this point B dash. Okay, so this represents the absolute velocity of point B, and this represents the tangential component of B with respect to A. Okay, and the direction is like this. Okay, so you can measure now this and this. Okay, from the scale. Now next step by joining A dash B dash, total total acceleration of B with respect to A may be measured and it is called acceleration image or acceleration diagram of link AB. Okay, understood?
Yes, sir.
Next is acceleration in the slider crank mechanism. Like velocity, acceleration in slider crank mechanism. Suppose let me draw it. This is the slider here, and this is the connecting rod. This is crank. Let us draw the imaginary circular path of the crank. So the crank is fixed here. Now let's say this is point O, okay, and the angular velocity is omega in this direction, clockwise direction. This angle is theta. Okay, this is point A. Okay, this is point B. Let us take any arbitrary point E on the connecting rod. Okay, and this one is the inner dead center IDC. This is the outer dead center ODC. Okay, and this is the velocity of point B with respect to O. Okay, this is the arrangement. Now, the crank OB, the crank OB makes an angle theta with IDC with IDC and rotates rotates clockwise direction, clockwise direction about fixed fixed point O, about fixed point O, with uniform as uniform angular velocity omega. Okay, so it can be termed as omega bo radian per second. Omega bo radian per second. So we have velocity of point B with respect to O will be defined as omega bo multiplied with OB. Let's say this is our equation 1. This we already know. Now radial acceleration, the radial component of acceleration of point B with respect to O, that is ARBO, is omega square BO into OB, or we can say B square BO divided by OB. Okay, this is equation 2. You remember these relations. Okay, now we got these two magnitudes using the empirical relation. Now we'll follow the step. The acceleration diagram may be drawn as follows. Okay, may be drawn as follows. I am writing the steps and you draw of yourself and show me. The next class, draw. I'll see your copy. O dash B dash vector parallel to OB. Okay, representing the radial component ARBO to some suitable scale, scale. Now second step, from B dash draw B dash X parallel to BA. Okay, the vector B dash X represents represents the radial component, the radial component, okay, of you can say A with respect to B, that is AR AB, which is equal to B square AB divided by BA. Okay. Now third step, since point B moves with a constant angular velocity, therefore Therefore, there will be there will be no tangential component of acceleration. Okay. Now next step is 4. From point X from point X draw X A dash, okay, perpendicular to AB, representing representing the tangential component AT AB. So this is the step to draw the acceleration diagram of a slider crank mechanism. So you follow these steps and draw the diagram. Show me in the next class. Okay.
Yes, sir. Yes, sir.